Okay, so which of these bulbs is more efficient? The bulb on the left takes in 24 watts of energy and it gives out 15 as light. The bulb on the right takes in 95 watts of energy and gives out 18 as light. So the bulb on the right is brighter because this is giving out more of light energy. However, which one is using a bigger fraction of its energy in a useful way? So to calculate that, I'm going to use the useful energy, which is the light energy, divided by the total that it's taking in. And you can see the bulb on the left is giving out 63% of its light in a useful way, while the bulb on the right is giving out 19% of its light in a useful way. So even though bulb B is brighter, bulb A is more efficient. So efficiency is the fraction of the total input that's used to achieve the purpose of the device. In other words, the useful energy. Okay, so the equation is efficiency equals useful output over total input, where you can use either energy or power for the input and the output here. Okay, and if you multiply by 100, you can get the percentage. Okay, so in this question, a motor is used to pull an elevator up from the bottom to the top floor, starting from rest and coming to rest at the top floor. So that means we don't have to worry about the change in kinetic energy. The elevator goes up a vertical height of 28 meters. The combined mass of the elevator and the passenger is 950 kilograms, and the total work done by the motor is 384 kilojoules. Calculate the efficiency of the lift. Okay, so we've got the total energy used by the motor over here. Okay, so and we want to figure out the useful energy in order to figure out the efficiency. The purpose of a lift is to increase your height. So that means in order to do that, you have to increase the gravitational potential energy. So the useful energy here is the gravitational potential energy. So I'm going to work that out using MGH, which is 950 times 9.81 times 28 meters. 261,000 joules. Okay, so you can see that's a lot bigger, smaller than what's actually been supplied. So the demand that's been supplied is, so if I take this 261,000 divided by the amount that's supplied, turning that into joules from kilojoules, and times that by 100, and that gives me 68%, which is reasonable. The kettle is used to heat water for a cup of tea. The heat absorbed by the water over 1.5 minutes is 115,500 joules. The kettle is supposedly 79% efficient. Calculate the power usage of the kettle. So they want a power here. So and they've given us the energy and time. So this 115,500 joules is actually the useful energy. It's the energy that actually goes into heating the water up. So I'm going to turn that into a power first. Okay, so that I could do it later, but I'm just going to do it now. Turning this time into seconds by multiplied by 60. So the useful power is 1283 watts. So that's the power that's actually going into heating the water up. So I want to figure out the total power that's used by the kettle. So this here corresponds to 79%. So to get 100%, I need to do 1283, chop up into 79 pieces, and multiply by 100. And that gives me 1624 watts. And that makes sense. It's taking in around 400 something joules more than what which is being wasted basically. Okay,